So I think we can start. So everyone, welcome to the third seminar in the seminar series organized by the Center for Technology Foresight and Policy, CTFP, at the Indian Institute of Technology, Jodhpur. So it is our pleasure today to have Dr. Manuel Baumann as our speaker for the third seminar. So Dr. Manuel Baumann is a senior researcher at the Institute for Technology Assessment and Systems Analysis of the Karlsruhe Institute of Technology, KIT, in Germany. He has a bachelor's degree in energy economics and a master's in energy and environmental management. His PhD was about the sustainability assessment of energy storage technologies. He is currently deputy of the subprogram Energy Storage, Techno-economics and Sustainability of the joint program Energy Storage of the European Energy Research Alliance, affiliate of Post Lithium Storage Cluster of Excellence, part of the EU Project Storage Research Infrastructure Ecosystem, and coordinator of other European and national projects. His current research interests are technology assessment, decision-making methods, techno-economics, and LCA, life cycle assessment of energy storage technologies. So with that brief introduction, let me welcome Dr. Baumann for this seminar, and thank you very much for accepting our invitation. And it is our pleasure to have you today as our speaker for the seminar series. Over to you, Dr. Manuel.
Thank you very much for the kind introduction. Nothing to add there. I will share my screen now. Give me a second. Does it work? Can you see my screen?
Not yet.
Okay.
Not yet. Yes, perfect. We can see our screen.
Okay, perfect.
Sure, this is fine.
All right. So we have 40 to 45 minutes, as far as I understood. So I
Yes.
prepared some slides towards the following topic, which is technology assessment and prospective systems analysis for emerging battery technologies. And thank you very much for the kind invitation to this seminar series, which I think is very nice to have such a format to stipulate also like international exchange on methodologies and experiences. As you see here, I have put some more names here because this work that I will present is not solely mine. It of course depends on the contribution of several persons that you see here. So I will skip this because I think the introduction was perfectly, so I do not have to repeat what has been said. The aim of the presentation is to provide you an overview of the Karlsruhe Institute of Technology, as well as of the Institute of Technology Assessment and Systems Analysis. Then we will deep dive into examples for life cycle oriented sustainability assessment for emerging storage technologies, and there I will show you some use cases where we work on and provide you some takeaways. So let's start. What is the Karlsruhe Institute of Technology? It's a research university in the Helmholtz Association. The Helmholtz Association is one of the biggest research associations in Europe, or no, not one. It is the biggest one, actually. And the Karlsruhe Institute of Technology was founded in the year 2009 as a merger of the former Research Center Karlsruhe, which was a nuclear research center, and the university, the Technical University of Karlsruhe. Yes, then they decided to call it KIT. And I suppose not everybody knows where Karlsruhe is. So here you have Germany, and it's like located here in the very southwest of Germany. And this is our institute, the ITAS in the center. So the KIT has several topics where they work on. The ones in bold are those which are the most relevant ones for us, at least in our group. It's climate and environment, energy, materials, mobility systems, humans, and technology. And just to give you some numbers from 2022, KIT has about 9,700 employees, of which I would say about half are really researchers, and the rest is technicians, and everything you need to keep research alive in an operative way. We have about 21,000 students, about 400 professors, and a budget of 970 million euros. So let's jump into ITAS. We are part of KIT. Here you see the team in the center, and the building in the back is our institute. It's an old bank building in the center of Karlsruhe. So also here, to give you a brief overview, we have a budget of about 9 million euros per year, with a third-party funding ratio of about 50%. 37 projects ongoing. The employee number is not correct anymore. We have about, I would say, 150 employees in our institute at the moment, with about 30 PhDs. And we have researchers from all abroad the globe. About 20 nations are represented in our institute, and we have 12 thematic research groups, and the institute is headed by Professor Armin Grunwald. So what are the tasks and goals of ITAS, the Institute of Technology Assessment and Systems Analysis? So what we do is to make research into the consequence of new scientific and technological developments and their science-based evaluation. That sounds a little bit abstract, but I will provide you some examples later on. Of course, what we do is to include the complex interactions between technology, science, and society in our research, because we want to provide orientation knowledge for the responsible design and, of course, the social embedment of new technologies, and to support, let's say, a societal benign embedment of those technologies. Of course, policy advice is one of the areas that are core in our institute, and also the participation in the public dialogue. Beside that, we of course also have a demand in further developing concepts and methods in technology assessment and systems analysis, which is then carried out in the different groups. So coming to our research profile, we really have a problem-oriented way of tackling our research. So it's really to provide knowledge for action. Here we work with value-based assessments with a commitment to transparency. That means, what does value-based mean here? That we conduct research towards sustainability, responsible research, and innovation, just as two examples. It's important for us that we have scientific independence, and we try to be excellent every day, every minute. And we see, of course, a high relevance of knowledge dealing with uncertainty. That is in particular related to future assessments, via scenarios or describing visions on certain technologies. In some cases, we have long-standing cooperations with other institutions from KIT. In particular, those institutions or institutes that conduct really the lab research, which develop the technologies and build them. We have a strong interdisciplinarity, so we really come from philosophy to engineering. Our head of department, Professor Grunwald, is a physicist, but then he became a philosopher. So you see, even our head is quite interdisciplinary. And of course, beyond that, we are even transdisciplinary because we cooperate beyond science. We, for example, have real-world laboratories, but you can check that on our website. What are typical topics that we have at ITAS? It's data information and knowledge. This is focused on let's say, the entire spectrum of artificial intelligence to digitalization. And there, the core question is, how can the digital transformation be used for the benefit of all? And you see here some focus areas. Then, that's the most relevant for me, sustainability and transformation of the energy system. Here we want to understand which local and global strategies are the most useful ones to assure a sustainable development of, for example, the energy transition here in Germany or Europe or globally. So then we have mobility as a further field. Here it's about tackling the future demand of mobility in let's say most sustainable way as possible. And here focus areas are sustainability of biofuel, socio-technical changes, urban research. Then we have participation in governance. This is a quite nice field. I would say it's also one of the core fields of ETAS. Well, all of those fields that I'm showing are relevant. But here it's mainly about how conflicts over future issues in technology and science can be resolved in a democratic way. And you see there are different focus areas here. I have to speed a little bit up because I've got plenty of slides and I do not want to get stuck to the, let's say, broad overview of ETAS. Then we have life and technology. Here it's about technologies that change biology, medicine, or or the human existence in general. The focus areas are biotechnologies, robotics and AI, human mechanization, responsible research and innovation. And finally, we have visions and ethics. How do expectations of the future and ethical considerations shape science, technology, and politics? Here we have projects on vision assessment, global ethics, and technology and innovation. So who are the ETAS addressees? Because we said, or I said, that we try to provide knowledge for action. It's, for example, the German Bundestag. That's the parliament in Germany, where we have the Office of Technology Assessment at the German Bundestag, the so-called TAP. Then we provide action knowledge to the European Parliament. Then, of course, the federal ministries that we have in Germany, the European Commissions via third-party funding. Then we have other federal authorities which we try to consult. Then we have state ministries of Baden-Württemberg. That is the state within Germany where we're located. Then, of course, we have corporations with companies and other associations. And then, of course, also we make use of the media and the public where we interlink with the broader citizenship. So ETAS, we have local activities, national activities, as you see here, and then international projects where we link to other colleagues all around the globe. And as I have mentioned it before, we have the Office of Technology Assessment at the German Bundestag. This is a unique, I would say, link to policy making. It's an independent scientific institution which is operated by ETAS, and it's situated in Berlin, next to the Bundestag here, where the chancellor and his ministers are doing their daily work. Here, we inform the decision, or we try to support decision making in the German Bundestag and provide here scientific information. The tasks and objectives are the analysis of the potential impact of new technologies, examination of legal, economic, and social framework conditions, and the identification of, let's say, opportunities within these different dimensions. Of course, this shall serve as a base to carry out actions for political decision makers. Here, you see an overview. What are the tasks? Being a radar, what are the new hot topics in technology development, etc. Show the consequences, provide orientation, communicating science, and stimulate a dialogue, and of course a networking aspect that we want to fulfill. And you can just visit the website. There are a lot of freely downloadable reports from the top. You can see it's really very different. Coming from genome editing, new space, etc. There are plenty of topics that are covered. But now let's deep dive. What does research at ETAS look like? And here I will give you, in a nutshell, an overview on technology assessment and system analysis. So as I have shown you before, this is one of the areas that we cover, sustainability and transformation of the energy system. And here we have several research groups. So philosophy of technology, research for sustainable energy technologies, etc. And I will primarily focus on the work that is conducted in the group RESET, Research for Sustainable Energy Technologies, because time is too short to really provide you an overview of this multifaceted work that is being carried out at ETAS. So what is RESET? Research for Sustainable Energy Technologies. This is the group. We are about 14 people. And what we do is to conduct sustainability assessments on emerging technologies to support decision making. And here we work with these fields. So we do environmental assessments, life cycle assessments. We look at the economic dimension where we conduct methods like life cycle costing. Then, of course, we look at the society where we have studies on technological acceptance, and we try to involve stakeholders as far as possible. Some technologies that we assess are batteries, power to X, biomass fuels, but today we're mainly going to speak about batteries. And having said that, why do we look at sustainability when it comes to batteries? Of course, all of you know that we have issues. We have climate change, we have planetary limits, and we have, for example, the Sustainable Development Goals, which we try to fulfill. And there are some regulatory there's some regulatory pressure for batteries and policy making in general in Europe, which is based on a European Green Deal. Then we have other developments like sustainable finance and taxonomy regulation. And when it comes to battery, we have a EU battery directive, which really regulates, for example, the carbon footprint of batteries. And it's always like the same question. We work in this field and we try to improve our state of living, and there are always those that criticize that. But at the end, it's important to consider these topics. And in our assessments, we try to follow different concepts. For example, we have the integrative concept of sustainable development, which was developed here over 20 years at our institute. We try to follow the sustainable development goals, and mainly due to operationalization issues, we use the triple bottom line model of sustainability. And as I said, we are looking at emerging technology. But what is emerging technology? There are several definitions of that. I will use one with this very nice definition that a PhD of us found, Merve Raksha. And emerging technology can be defined as a radical, novel, and relatively fast-growing technology characterized by a certain degree of coherence, persisting over time, and with the potential to exert a considerable impact on the socioeconomic domains. Its most prominent impact, however, lies in the future, and so in the emergent phase is still somewhat uncertain and ambiguous. From this result two questions for the sustainability assessment. The first one is to find the right shape targets. So if we want to have a sustainable technology, how do we have to shape the technology? Do we have to optimize it toward environmental dimensions, economic or social dimensions, and how to characterize these and quantify these? And of course, to steer the development of emerging technology and to improve the sustainability before technology entrenchment limits the potential for intervention. I will show what that means in a later slide. So emerging technologies are for sure batteries, and in particular lithium-ion batteries. All of you know lithium-ion batteries. There are several chemistries available, and there are always new announcements. So just like I think at the end of last year, CATL announced that they have a new battery with a very high energy density, and the lithium-ion battery is a really disruptive and emerging technology, or was really disruptive and is still emerging. Yes, and how would the world look like if we would not have lithium-ion batteries? So we would have mobile phones like that, electric vehicles where the battery is here set at the back, or we would have laptops where the battery is attached like with an external device due to the big size of the same. And lithium-ion batteries or new batteries are fantastic, but there are issues. And these issues are related to sustainability. You have doubts about the use of vulnerable raw materials, like you all have heard it, for example, cobalt, nickel, lithium. The production cost and life cycle costs are still too high. There are environmental and social impacts of production. The technological performance needs improvement, recycling issues, safety issues, and you can name it other aspects. But for sustainability, it's mainly due to the, I would say, extraction and purification of lithium and cobalt, depending on the chemistry, or here of nickel, just to give you some examples. So the topics for sustainability assessment along the life cycle of batteries, as you see here, there's an article available on this, is really starting from raw materials, the design of the battery, the production of the same, the use phase, potentially a second or third use phase of the battery, and recycling at the end. And if we are doing these assessments, it's always important to understand that there are important factors for energy storage, which is energy density, power density, efficiency, safety, cost, sustainability, and many more. But what we have learned, or it's a fact, is that there is no perfect energy storage solution. There is at all no perfect technological solution. You always will have some trade-off that is necessary. For example, if you want to have a high capacity battery, it will not have a high durability, for example. Or if you want to have high environmental standards, the cost cannot be low, depending on how you include them. And a major problem in the development of sustainable technologies is a time, power, and control dilemma, which is the so-called Collingridge dilemma. If we look at the different technology readiness levels, maybe some of you are familiar with them. It starts with one and goes to 9. 1 means a technology is being investigated regarding its basic principles. And you see then, for example, in TRL4, you have an experimental pilot, and 9 is then when you really have a successful working system that can be introduced into markets. So over time, the potential for sustainable design goes down. Here we have a lot of degree of freedom to design our technology. And the cost for adjustments is low, but over time, the potential for sustainable design goes down and the cost for adjustments goes up. Why? Because we have here a kind of entrenchment. So here, when we have a full proven industrial manufacturing line, it will be very costly to adjust it to become a more sustainable, let's say, production process. So we have really a time problem here and an growing entrenchment in the development of technologies. And this leads to a Collingridge dilemma, which is, on the first hand, you have an information problem because the effects are difficult to predict until the technology is fully developed and widely used. That means at the beginning of the development phase, we only have a few information and technology. This becomes more over time, of course, because we can collect data, we see how it's operated, etc. At the same time, we have a power problem. The degree of freedom is being minimized over time. Yes, that means here, when we could do the most, we don't have the data to do that because we do not know what the impacts are and we do not know how the performance of the technology looks like. So you have two trends that are not running in the same way. So here, the power problem in early stages of a technology's development, there are numerous control options, but the choice of direction is difficult. At later stages, this relationship is reversed. Of course, you have here a high risk of failure of the technology, and here not a low risk, but a lower risk for transition into markets. And if it comes to sustainability, it becomes complex. You can use this, I would say, rather engineering thinking like structuring of problems. So if we have, let's say, only a component that we're looking at developing a new cathode material for a battery, we might have a so-called tame problem. So the problem and the solution are clear, and we only have a limited amount of stakeholders that we have to involve there, like technology developers, chemists, etc. But if it becomes more complex, like we want to build a new sustainable storage unit, it becomes more complex because we have more factors that we have to consider, more components, and we might have more experts that we have to involve, each with its own expertise. Then, of course, uncertainty is also increased here. Then let's say the highest degree is then when it becomes a wicked problem. What is a wicked problem? It's when you have when neither the problem nor the solution is clear. That means by looking at a complex problem like the energy transition, we identify new problems, yes, and we have to find new solution paths. So it's always like an iterative process. It's a never-ending process. We always have to reconfigure our way of tackling the problem and to understand it also. And there is no best or worst solution. So we always have to keep on iterating. And here we use something called constructive technology assessment, at least in our group. The objective of this framework, I would say, is to analyze the effects of scientific and technological developments and the associated social, economic, and ecological opportunities and risks. So what happens here if we have a new technology? We have, let's say, one group, which are the so-called enactors. Those are those stakeholders or who create and enact new options, technology developers. They work in their technological domain. They have, let's say, more narrow criteria in the development of their technology. And on the other hand, we have so-called selectors. They are, for example, end users, NGOs, whatever you want. And they have a rather comparative thinking, a generalistic focus. And we try to put them into dialogue. Yes, we try to serve as a broker, you can say so. And we try to steer technological development and give some space for interaction. And to do so, we have different assessment methods like life cycle assessment, multi-criteria decision-making, technology foresight, socio-technical scenarios, and so on and so forth. Within our group, we mainly focus on sustainability assessment methods. One of the most important ones is life cycle assessment. Then we have life cycle costing and social life cycle assessment and other ones, which I will not go into detail. But I think here the life cycle assessment, material flow analysis, environmental, carbon, water footprint are different indicators that can be used here is the most important ones. And also this way of thinking, life cycle based sustainability assessment is important. Why? Because any environmental, economic, or social assessment method has to take into account the entire full life cycle of a product, just to be able to identify potential hotspots that might occur during one of the different steps, life cycle steps of a product. So it starts really with natural resources, extraction of raw materials, production, use and maintenance, disposal and recycling, or emissions. And here you have different frameworks where you can integrate the different dimensions, environment, economy, and society, and conduct, sorry, something like a life cycle sustainability assessment, where you combine this different life cycle oriented methods, LCA, LCC, or SLCA. And just to give you a brief overview, these methods share more or less a common approach. And it's standardized, at least for LCA. You always start with a goal and scope definition, then you go to an inventory analysis and an impact assessment and an interpretation. And it serves for process development and improvement, public policy making, and other aspects. Here you see it in a more detailed way, goal and scope definition. We try to identify what's the goal of our research. Then you have different things that you have to consider. Here, the inventory analysis, here you try to come up with inventory modeling, like to build up all the or to collect all the data that you need to carry out your assessments. And then at the end, you link it to the different impact categories that you have, and you try to make an interpretation. And here, one major step is the inventory analysis. This is the part where you collect data. And it's the most crucial step for all the methods that I have shown you before, because we always start like data collection, no problem. But at the end, there is no data. It's a classic. Every PhD that starts within our group struggles to collect the data that he needs. Then, of course, we have the impact assessment. The impact assessment here, this is a little bit drastic, is, for example, climate change, eutrophication, land use, etc., where we also have to understand how the relation of these different impact categories is. For example, a high impact in climate change um, might be very different if you go to human toxicity, which might be very low for a product. I will show an example for that later on. And then we come to the interpretation phase, which is, I would say, the most difficult one beside the yeah, well, all steps are difficult, but it's an iterative process. So this is not sequential, what I have shown you. Everything is iterative because we have to understand our results and the impact assessment, go back maybe to the inventory analysis and maybe also reformulate our goal and scope definition. And here in the interpretation, classically, this element occurs, the element of which is the element of confusion. So also here, it's important just to get into the doing with an assessment to understand the results, to reshape the data, and so on and so forth. And if we look at into emerging technologies, it's quite difficult because it is not like looking at a standardized existing project. So you have here, for example, in a high TRL at this time, an existing mature technology and a current system and production scale, of course. And if we look at emerging technology, we have a low TRL. So you just cannot scale it up like in this same time. Rather, you have to think in a scenario, how will this technology be implemented? How will it be produced? And of course, not at the low TRL, at the high TRL, yes? And this is quite challenging because this new technology might entail radical changes that might not occur now, but in, let's say, 10 years. And from this, different challenges occur. Data-wise, we have, as I said before, low data availability, poor data quality for different foreground and background processes. We have to conduct a scale-up. This can be very difficult. There are several methods available. Of course, we have uncertainty, which we have to deal with. Model uncertainty, scenario uncertainty, communication of the results with stakeholders has to be carried out very carefully here in order not to provide a wrong picture, and the comparability. So we have to consider what are the functionality and characteristics which we might not know in the future, for example. What are the differences in functionality compared to existing alternatives? What are the differences in system boundaries? So these are just some aspects that have to be considered. And here I have to do some advertisement. We just brought out a book, we edited a book where you can take a look at these different methods and challenges. It's called Emerging Battery Technologies to Boost the Clean Energy Transition. Here we have a section which essentially just deals around with these questions that I just formulated before. Now I would like to come to the use case of sodium-ion batteries, just to show you some works that we conducted. What are sodium-ion batteries? Sodium-ion batteries are a new type of battery which works yeah, in the same way like a lithium-ion battery. You just use sodium instead of lithium in the cathode active material and electrolyte salt, and you use aluminum instead of copper for the current collector on the anode side. And you can also use several cathode materials. So they're same, but different. The anode materials, lithium, graphite, metallic lithium, or in comparison to sodium-ion batteries, you use hard carbon. You can also use metallic sodium. And you have also here like nickel, cobalt, manganese, whatever you want. And also here nickel, manganese, yeah, titanium, aluminum, etc. And the question that we always have here, how to compare sodium-ion batteries with lithium-ion batteries. If we look at the different steps to produce a cell coming from material level to the end of life. So we have here a material level where we have active materials. We manufacture some electrodes with binders, collectors, conductive additives. Then we build a cell. Then we build a module. Then we build a pack or a rack. Then there is an application at the end of life. In the following, I will show you some use cases, not all of them, just two, to provide you a, let's say, first rough idea of how we try to to tackle like this uncertainty issues and to provide feedback to our peer group, which depends then also always from the project context. The first case is a material screening where we conducted a sustainability screening of sodium-ion battery cathode materials. The target groups were technology developers, and we have a very high uncertainty here because we are dealing with a very low TRL. There is an article available for this, and you can see it here and go into that if you want to. And we just focus here on the material level. The cell level is not considered. So how did we do that? We screened 42 cathode active materials with 3 simple indicators: cost, carbon footprint, criticality. And we had to use theoretical data, literature, and electrochemical calculations. And here's the framework. And I have to tell you, we started very naive with this task. Like 3 years ago, within a project, we said, let's do a screening of your activities where you're developing different cathode materials at KIT, like the guys from the lab. And we thought it shall be a very fast task. It took us at the end 1.5 years to come up with an assessment. And we just had to discuss a lot on this different criteria because we had such high uncertainty. We had to use very simple indicators that are useful at this very initial stage of the development of a sodium-ion battery. So we separated the cathode materials into acidic and polyanionic materials and benchmarked them against the corresponding state-of-the-art lithium-ion battery systems. I don't know how many of you are familiar with batteries, but NMC 62 is nickel, manganese, cobalt. Um, one generation before. I think now it's 811 mainly being applied, which is mainly used in electric vehicles, and the lithium iron phosphate battery for this other type. As you see here, we compared 8 lithium cathode types with the 42 sodium ion cathode types. We calculated the energy densities, looked at the raw materials, and then we indicated in kind of traffic light system potential hotspots in the development. Here are the results. The results for cost in euro per kilowatt hour of cathode materials. And I will not go into detail to this massive table, but what you can see here is that you have the lithium iron phosphate, the lithium chemistries here, and in comparison to that, the sodium ion sodium ion battery cathode chemistries that we analyzed. You can see here that are the benchmarks, the two that they perform quite well. And you see here the share of cost depending on the different materials that are used in the corresponding electrodes. Long story short, we saw that cobalt, nickel, and vanadium are key drivers for the carbon for the not the carbon footprint. It should be here the cost. However, we saw that there is a surprisingly good correlation between the three indicators that I have shown you before, but there's a high uncertainty in the results here. The results for the carbon footprint are, I would say, comparable. The carbon footprint is the CO2, the kilogram CO2 equivalents per kilowatt hour of cathode material produced. And also here, we can see that again, cobalt, nickel, and vanadium are the key drivers for the carbon footprint. And again, we have a very good correlation to the other indicators. The criticality, though, is in particular out of a European perspective, very important because Europe doesn't have any substantial resources when it comes to batteries. We don't have lithium. We have lithium, but we're not mining it, at least not in the amounts that we would require. And that's why resource criticality is something very crucial in Europe because we have to import most of the resources. So there is an indicator called supply risk. It's a composite index which describes the risk of a disruption in a supply of a specific material. And that is always based, of course, on a, let's say, on a certain scope. For example, the US or the EU, they will have different supply risks. And here you see also the evaluation of these different materials out of the supply risk perspective. Again, cobalt, nickel, and vanadium are the main problems for the supply risk. though this is very difficult, right? You have three different indicators. So what do you say then to the technology developers? So here we try to do a tentative ranking to provide them, let's say, a priority list of chemistries that should be further investigated. And we came up here with this ranking. And we saw that there is a group of chemistries that provide good results, and we did some sensitivity analysis here to check the robustness. At the end, there's high uncertainty related to this, and we also did then here, but I'm not showing the slide, some extrapolation to the future. How will the cost evolve? How might economies of scale impact the results to provide here a view into the future. The next use case was an LCA study, the prospective LCA of sodium-ion batteries. Again here, our target group were technology developers, and we had a high uncertainty. And you can find the detailed results here in this article. I think I have 5 more minutes, but I will manage. Also here, the system boundary was like covering these steps. So active materials, electrode level, cell level, and application level. And what we did is to conduct a life cycle assessment of sodium-ion battery cells, where we included manufacturing use phase and end-of-life phase. And I will show you like the impacts of this technology of, I think, 5 different alternatives related to their global warming potential and abiotic resource depletion potential. The abiotic resource depletion potential is an indicator for how much metallic non-fossil resources are depleted when you manufacture such a systems. These are the cells, sodium cells that were investigated, and here the reference cells. And here it started. There was no data available, so we had to build up our own model. And again, a model is, of course, it's theoretical, but it's freely downloadable, so you can take a look at it if you want to. I'll jump into the results. Again, you see here the results, kilogram CO2 equivalents per kilowatt hour cell capacity. And what you can see here is that the sodium ion batteries in terms of global warming potential necessarily do not perform better than their alternatives, the lithium ion batteries. Interesting here is when you go to another indicator, the abiotic resource depletion, the picture looks completely different. Here, sodium-ion batteries mostly outperform lithium-ion batteries completely. As you see here, same systems, different impact category, completely different results. So this is what I meant with the trade-offs before. If you have different indicators, you will have to go into interpretation and think, what do I have to tell to my peer group what these results mean? So in the next step, we decided, okay, let's look at the different recycling paths that are possible, because we would be interested, like if we recycle the cells appropriately, like with high-end recycling, what would happen? Again, recycling is always considered to be environmental friendly, but here we saw for the global warming potential that no, for the sodium ion batteries, if we really go into highly advanced recycling, getting out every component of the cell, we have a higher carbon footprint in relation to simple recycling methods. In relation to this, let's say, bad lithium, nickel, manganese, cobalt battery, which then performs better. The sodium ion batteries showed to have let's say, a worse result here. Again, for the abiotic resource depletion, the picture is a little bit different, but I have to mention here that we just included a very idealized way of recycling, so it's theoretical. Last use case, just to give you a different picture, we looked here at the acceptability of battery storage. There are different articles available here. And here we wanted to go beyond pure technology development and understand what are, for example, acceptability issues when it comes to the implementation of large battery storage facilities. Sorry. So what we did here, we made a survey because we saw that there are several studies available for technical, economic, and environmental factors, but social acceptability is a key condition for enabling a smooth rollout of storage technologies, in particular of large ones. So we carried out an online questionnaire to capture in a qualitative way, I would say, the public opinions. And there's also this article which you can take a look at. And here you see we looked at the visual impact of the systems. How does this affect the acceptance, the location? If we would build it in a neighborhood, in a residential area or industrial area, what are the implications when it comes to acceptance? Here you see the two different images that we provided to our participants, and then they could make or fill out the survey depending on their impressions. So you have here this rather industrial design of a container, and here the integration of the storage system into a fancy building. The results, in short, just one aspect that I want to show you: how can social acceptability of large stationary battery storage be increased? And we saw here that there is a ranking of the mitigation measures that can be included in residential areas, which is the most critical area in terms of acceptance. And we saw here that ensuring the proper recycling was perceived as very important, observing strict environmental and social standards. And then here the lowest one was providing a final compensation to those living inside was ranked the lowest. However, you can take a deep dive into the article if you want to. To come to an end, what are challenges regarding transferability also to other cell technologies or technologies in general? I showed you an assessment on a material level. The results that I showed you here are just valid for a certain material. They can be very different on a component or system level. There is also high uncertainty when we look at the manufacturing processes. It's very crucial to consider where it's produced, how it's produced, and also to consider transport routes here. Then the performance. This is a very hard task because often we do not know how's the efficiency of the cell, how's the lifetime, etc. So here we have to work with, for example, parameterization, etc. Then, of course, recycling. We have to include that because it leads to a completely different picture. Because sometimes, as you have seen, primary sourcing for abundant materials might be out of an environmental perspective more efficient. And the result interpretation has always to be carried out very carefully, and all relevant life cycle stages should be considered. Takeaways from ITAS. So that you keep our institution in mind. We try to research into complex issues, the interplay between technology, science, and society. We are inter and transdisciplinary. We work on concept and method development. Sustainability assessments cover materials to system level. And we want to generate practical knowledge on a technical and systemic level. And we have a broad orientation towards EU level, global level, federal and state level, and industry. Here are further use cases that you can take a look at. I think I will send the presentation later on to you, Professor Kumar, so you can take a look at it. Thank you very much for your attention. I think I took 5 minutes too much, and I'm open for questions if there are any.
And thank you. Thanks a lot, Dr. Manuel, for the insightful talk. So now we have open for questions.
If there are no questions, even better.
So basically, you're talking about these early stage technologies, right? So what do you think are the key challenges by looking at technologies in the early stage with the low TRL, say, between 4 to 6? Because we have to do life cycle assessment repetitively, it becomes iterative, especially when looking at the inventory stage and when fixing the functional unit and things like that. What do you think are the key challenges involved?
And the low TRL levels, I would say the key challenge is really to become an to collect the data, because this is the struggle that we always have to have let's say appropriate information on for the technology when it comes to manufacturing of the same. Here, for example, everything below TRL 6, we do, for example, measurements in the labs. So we measure the energy flows and material flows. And then, of course, as it is very individual on a lab scale, we have very high impacts. Yes. So here we deal with a high uncertainty because each lab performs different and has different sized, let's say, dry rooms, for example, when it comes to battery technologies. And then we have to use this information and upscale it somehow. So this is how we proceed. And a big challenge also is when we have new projects and we have to get into a dialogue with the colleagues that are performing the research on a lab scale, is to provide them a basic understanding of what we're doing. Yes, the wording. So what can they expect from us? What do we need? How can they help us? So this proves or has been always a factor that took us a lot of time. I think these are the main challenges, of course. So data, communication, and then to extrapolate this information on a lab scale to higher TRLs.
Right. So, do you also feel that conventionally life cycle assessment has been kind of, I mean, it does not take into account the time factor, right? It does not take into account dynamic within, especially by looking at technology assessment, things like that. So, how do you think time as a factor can be taken into account while looking at emerging or futuristic technologies?
Yeah. The aspect of time, of course, in LCA, this would be, for example, changing electricity mixtures. So in the assessments and the prospective assessments, we try to include that, for example, via different scenarios, assuming, well, this technology will be produced in 2030. So we assume the corresponding electricity mix there. Then, of course, how could the background systems change? Then also, if you have to produce some steel, might it be via a different route, or do you use I don't know, carbothermal reduction or some kind of carbon-free reduction of iron? Just as an example, these are things that we have then to consider. And there it comes really to building up different scenarios for the assessments. And these scenarios have to be transparent and robust. They have to be also feasible, of course, but that's always difficult.
Right, right, right. You're absolutely with that. Right. So we have a question.
Yeah, can I ask?
Yeah, yes, please. Go ahead.
When we are talking about this life of these batteries, can you comment the effect of extreme climates on these life of these batteries? For example, like extreme hot climate of desert or extreme cold climate, and what are the technological development which is taking place to make their life more sustainable, more reliable in the extreme climates?
For the batteries, you mean? Okay.
Yeah, for the batteries.
Mhm. Yeah, that really depends on the chemistry. I would say some batteries are more prone to high or low temperatures, but you of course have to then adopt regarding the periphery. For example, here you see still my screen. This left block, this is for example a storage system that we have at the campus north, where we have a active cooling of the system. So if you have a very hot region and you use lithium-ion batteries, you should assure that there is some climatization in order to improve the lifetime of the cells. So not to have a container where you have 60 degrees Celsius in it. So to have some cooling there. On the other way, if you are somewhere in Scandinavia with very low temperatures, you have to heat the battery. So climate within the building or the container here plays a relevant role. And if it comes to life cycle assessment, this is a big question mark. How do you consider, for example, the energy demand in different climatic areas on the planet? So if you do an LCA, for example, in a sub-Saharan zone, you have to consider for sure different lifetimes if you do not have an appropriate cooling system for your battery.
No, I was specifically asking the questions regarding the extreme hot climate of desert. So
Yeah.
how can we, so and for the field applications? where the container and these things may not be available. So can something be done to improve their life?
Yeah. And you mean the battery, hot climate in a desert? Yeah.
Yeah.
And if you're not able to regulate the temperature.
Yeah.
Whew. Yeah. How do you handle that? For sure, try to maybe have an appropriate battery management system with according C rates and depth of discharges. I think there are ways to optimize it, but at the end, I'm not a chemist. But these are measures that I would propose then. If you're not able to regulate the temperature in extreme areas, or you use chemistries that are more robust, like instead of NMC, lithium iron phosphate, for example.
Okay, thank you.
Thank you.
Hi, Mr. Manuel. So it's a very nice talk here from you. I have one last question regarding the difference between, or how can you differentiate between the lead acid and the lithium ion batteries?
Okay. Yeah, the lead acid battery and the lithium ion battery. I mean, the lead acid battery is the oldest, is the mother of all batteries, and has a long history of development. The energy density is the biggest difference, I would say. For a lead acid battery, depending on the type, you have, I don't know, 30 to 50 watt hours per kilogram versus a lithium ion battery, which has 250, 260 watt hours per kilogram. So here the energy that can be carried per mass unit is very different for those two systems. On the other hand, the lead acid battery is a very simple system in relation to a lithium ion battery. You can easily dismantle it, you can easily build it. A problem with lead acid batteries is that you have lead in it, which is highly toxic. That's why in Europe it has to be recycled. That's due to the high environmental impact and advantage, actually, because recycling rates of lead acid batteries here are up to 98%. And this avoids that any lead goes into the environment. Lithium ion batteries, though, are more difficult to recycle. Yes, so you need more process steps, more energy to get the valuable materials out. The lead acid battery also is cheaper in relation to a lithium ion battery when it comes to production, not the lifetime, because you have not such a long lifetime like a lithium ion battery. For example, a lead acid battery has, in terms of cyclability, cycles, full cycles that such a battery can run, depending on the system, 100 to 1000 cycles. Depending on the chemistry, a lithium ion battery can have cycles of up to 10,000. Yes, so that's, I would say, one main difference. In terms of, environmental impact, there it becomes interesting, because if you consider recycling and different impact categories and the application, lead acid batteries can be very competitive in relation to lithium ion batteries.
Great. So yeah, I agree. Thank you. Thank you so much.
Thank you. Okay. Any further question? If not, I would stop sharing.
Yeah. If there are no other questions, let us once again thank the speaker, Dr. Manuel Baumann. And it has been great having you today as our speaker for the seminar series. And we look forward to engage with you in the future.
Thank you very much for the invitation. It was a pleasure. Have a nice day. And one last question. Shall I send you the presentation?
Yes, you may share with me so that I can circulate it.
Yeah, Perfect. Okay.